Welcome everybody on Zoom. Welcome everybody in the lecture hall. This is week 14. This is the last week. And hopefully this is even the last lecture, meaning that you get tomorrow free. So of course, the last lecture is always special, as you can notice with the bow tie, and the quiz game that we are going to play hopefully in the second hour in order to test your knowledge. I will explain that. But before we come to that, in the first hour, I hope to complete a few things. One of them is to tell you about one last thing on performance at large scales, then I'll do a wrap up. So the performance at large scales, I spread it over multiple weeks. In the first week, I told you about the bottlenecks. You have to find the one bottleneck that is slowing down your system. In the second week, I told you how you can improve specific bottlenecks once you have identified the bottleneck, otherwise it's useless. And in this third part, I would like to show you something very strange that many people don't expect and very often only discover once they are working in a large company with big data centers. Comes as a surprise. It's called tail latency. It's like a special relativity effect of large-scale databases. So what is this? Well, remember this whole thing we've been doing with Spark and MapReduce and so on, where we have tasks that are supposed to be done on data. So we split the data into chunks, and every task means processing one chunk. Then you have slots that are the resources on your cluster, and you assign tasks to slots dynamically, right? So you usually have more tasks than slots, maybe, I don't know, twice, 5 times, 10 times, sometimes more. In an idle system, every slot is going to finish at exactly the same time. That's too ideal, right? In the real world, you would expect something more like this, because if you spread the tasks over the cluster dynamically, you should even things quite well out, and this is what you get. So at large scales, that's what we should expect, right? Of course, with many, many more, like thousands, tens of thousands, hundreds of thousands. Yes, actually no. Because as soon as you enter very large scales and you have 4, 5, 6 digits numbers of tasks or machines, then you're going to have one of the machines that's going to take forever and everybody's waiting for it. And it's like it doesn't even end. This is blocking your entire query. And this is a big deal because, you know, if it wasn't for that very machine that's blocking everything, that's called a straggler, I think is another term for that, you basically are stuck with the entire query that cannot return just because of that one machine. Very frustrating. First, I need to tell you why that is. It all has to do with the fact that machines are a complex ecosystem. A cluster is a complex ecosystem. The resources are shared. There's a lot of operating system stuff that happens on the machine that I don't know much about because I'm not an operating system person, but I know that there are things like you switch the threads, you have multiple processes running on the same CPU, you have garbage collection, you have plenty of stuff. This is all because resources are shared. So you need to alternate a little bit between them. The same goes globally. You have a distributed file system, you have the network switches and so on. And so what happens is that there are all these things that happen in the background and that I don't really understand and don't actually need to understand. All I need to know that this is happening. It has to do with power, with garbage collection, with energy management, with queues and so on. You have daemons running in the background that can create hiccups. It's totally unpredictable, but it happens. And when that happens, then the machine is basically has to stop for a while or wait until this completes, right? So once you have understood that there is this, that's happening once in a while, like bad luck that triggers, you can think in terms of probability theory. So imagine I'm looking at just one machine here, one machine. And imagine that I'm assuming that my goal is 1 second. So this is my metric. I want to be done in 1 second. And that one machine is going to be done in less than 1 second in 99% of the cases. Meaning that if I throw 100 machines at it, one on average is going to take longer than a second and 99 will not, right? Another way of expressing that is that the 99th percentile of the machines completes in less than 1 second, and there's just a tiny percent that doesn't, right? Okay, but this is a single node. So now you probably visited a few probability theory lectures, and you ask yourself, okay, now if I have, for example, 100 nodes or 1,000 nodes, what's the probability that I'd have no problem at all, right? Well, that's an intersection And nothing must go wrong. So nothing must go wrong here. Nothing must go wrong here. Nothing, right, that's a tongue twister. Nothing must go wrong there, and so on and so on, right? So you multiply the 99%, so it's 99% to the power of n. And if you have 10 nodes, you're already around its approximative at 90% of the cases, but not exact. That's one of the things you learn in high school, to be careful with the powers. If you go all the way to 100, wow, this hurts. 37% of the cases, all the machines will be known in less than 1 second. In 2/3 of the cases, there will be one of the machines that takes longer. 1,000 nodes, it's absolutely awful. Here, you can consider it guaranteed. 99.9999% of the cases, it's a guarantee almost that one machine will take longer than a second. This kills your entire system. So of course, when that happens, and this is what typical junior developers start doing in a company, of course, they visited their lecture, they know what to do. So they try to improve things, right? So, before I get to that, I wanted to show you the same thing if I try to switch the probability. Imagine that you could improve things, that you could do something better. And now your less than 1 second is 99.99% of the cases. So you might think, okay, now the problem goes away, right? That's for a single node. So now I compute it with 2,000 servers, so 99% to the power of 2,000. I'm already down to 80%. So in 20% of the cases, I have the problem again, right? So basically, I cannot get rid of the problem. These are nice curves that were contributed by, I think it was Jeff Dean in a paper of tail latency, that this is if you do the computation with 1% of the machine that take forever, right? And then this is the number of servers. And here it's the probability that it takes more than 1 second. So you see, if you have 1% of chance that it takes more than 1 second, then it very quickly goes all the way up to 1, that it takes forever. Now, if you try to improve to 99.9%, 1 in 1,000, the curve shifts a bit, but it still eventually goes to 1. And this is not so many machines. This is what you have in a data center. But even if you go like 1 in 10,000, so this is 99.9% for every node to take more than the time you want, so 1 second, the curve is still going up. It's more linear here, of course. You can do the math. It's still going up, and this is still unacceptable. If you're a service online, you cannot just fail the Google search or the Yahoo search or the Bing search or the DuckDuckGo search 20% of the time. That just doesn't work, right? So you cannot. This is not a problem. This is a problem. Sorry. So if you try to fix things, you can try to do things on the hardware. You can try to optimize your code, because you know that writing better code is going to improve the performance. You can try to better manage the background activities and so on and so on. You can try all you want. This is still going to happen. All you can do is modify this probability P, so basically the curve, but you still have the problem. It doesn't go away. So this is why this is the reason why you need other solutions to fix that sort of problem. And one of the solutions that was actually suggested by the companies that had these issues is that, for example, you can duplicate all of your tasks. You do all of them twice, you duplicate everything, and then you just pick whoever is first completing and then stop the other once it's completed. This is one way of doing that. So the first slot who completes a task is winning, and then you delete or stop the other slot that had the same task. This is one way of dealing with the problem. And another one is a hedge request that is more subtle. You basically let the system run. And what you do is that you let it run to the point that it's lower than, for example, 95% of the cases. So you go to the 95th percentile of slowness, so to say, and once it's lower than 95% of the machines, then you stop it and you duplicate it and launch it again. So this is slightly less resource consuming, because here you don't duplicate everything as we did here. That's the first solution. You only duplicate when you notice that there is a straggler and it's blocked at the 95th percentile of duration. The 95th percentile, it was redundant, and then you launch a duplicate task. And actually, it was tried. So in the paper, again, there is in Moodle the reference to that paper. They tried it, And for example, they realized with that data, so they sent 1,000 requests, they had 100 servers, they decided to hedge after 10 milliseconds. So this is the whatever 95th percentile that they picked. And it went down from 1,000 milliseconds to just 74 milliseconds for the 99.9 percentile, because of course it's probabilistic, right? You don't have a definitive duration, but basically it was faster than that in everything but once in 1,000, right? So once in 1,000, it's worse than that, but other than that, in 999 cases out of 1,000, it's at least like that. And you see here the improvement from 1,000 to 74. And what's the cost? Because there's obviously a cost to pay, is that we had to re-execute 2% of the request. So we needed to add two more percents. Is it a question?
Yeah, there's one question. Could we also duplicate tasks to other nodes as soon as they are done with their tasks?
The reason I'm not quite getting the question, because once a node is, there are so many tongue twisters today. I don't know what's happening to my voice. So once a task is done on a node, it's done, right? You don't need any more to execute it. When we duplicate a task, it's before it's completed, right? Because we don't know if it will succeed or not. Does it make sense? Or is it something maybe I didn't get in your question? Or if another node finished its task, but then we don't have to duplicate that task again, right? It's done by the other nodes. Maybe could you reformulate so we can reuse that node for the other task that runs longer? Oh, I think if I correctly get you, this is the spirit, right? So basically, if you notice that this is what's happening here. If you notice that one of the nodes is taking forever, or one of the slots, if you want to use the same vocabulary, it's taking forever here, so it's kind of lost. You almost have to declare it as lost, and that's it. Then you are going to wait for the next idle slot in here, and then as soon as another slot becomes idle, then you use it to duplicate the task. Maybe this is the meaning of what you are saying. Yes, exactly. So you got it correctly. That's exactly the idea. Right. So I repeat, once a slot takes forever, consider it lost, it's gone, and just reallocate the task a second time to the next freely available slots. Okay. And that's pretty much it. So you see, it's more like a curiosity that I wanted to show you, like the sort of things that you wouldn't have expected and that actually happens at these large scales. Yes? I will repeat the question. So the question that you are asking, it's a practical question, if I got you correctly. You're asking how you get these percentiles. I can only guess, because I haven't myself directly put my fingers in these things. But the idea is that I could imagine several things. It might be that you have a system that is in cruise mode. You have millions of customers that keep using the system every time. And so you have, after a few weeks, you have so much data that you get your Gaussian curve or whatever curve that is, right? And then you know the percentiles out of experience. Now, in the case that you don't really know the request in advance, that's tougher, because then you basically have to guesstimate the percentiles, and then it's a whole other problem. I consider it out of scope of the discussion here, but I could imagine that then it's tougher if you don't know yet. But I think in practice, I mean, if you look at companies, what they do is that they operate a business that is basically in cruise mode every day, and they just want the business to keep working. So that would be my guess. But Probably there are people who have this issue of estimated, and I could imagine, I don't know if you get into Bayesian reasoning or if you can have something fancy, or if you just start gathering data and just use as a sample what you have so far, and you just use it as an estimator for the real thing. Did I answer your question? Okay, awesome. That was pretty much it actually for what I wanted to show about performance. All right. Okay. That's strange, right? It's not the sort of things that you would have expected, because normally you would expect if you fix the code, you make it faster. But no, that's not how it is. You do have these stragglers that just take forever. Okay, so I'm going to stop here and now go to the wrap up.